So moving on then, let's look at the momentum equation. So we'll do the same thing for momentum. This is the momentum equation we derived when we went through the control volume analysis, like way back, right? So we got to this equation. What we want to do, though, is this equation is, if you remember, you probably don't remember, but what we did was we derived all the terms, and then we went through some algebra. We got to a point and I said, OK, there's some steps that you can take to further simplify this last term here down to this. It turns out the form before this is the one that's actually useful for our models of turbulence. So let's go backwards a few steps to get to the right equation, and then we'll start working with that. So I'll just show you kind of how we get backwards. So what we're going to do is we're going to use the definition partial u, partial x, plus partial v, partial y equals 0, just from continuity. So we're going to use that definition. And we're going to note that these two together equal 0, right? They, by conservation, equals 0. So if I add this term to this equation, it does not change this equation. Right? We're adding something that equals 0 to the top equation, so it's not going to change it. But it's useful algebraically to help us express things the way we want. So we'll add this in. It becomes the following is the rho times partial u partial t plus u partial x plus v partial u partial y is equal to minus dp infinity dx plus mu partial squared u partial y squared. But I want to add in this term. So what I'm going to do is over here, sorry, I should have left room. On the left-hand side, to the left-hand side, I'm adding this term. So I'm going to add in what? I'm going to add in rho times u times this continuity term, partial u, partial x, partial v, partial y. So sorry, that's a little confusing. This stuff all over here equals that stuff. OK, so I haven't changed anything about the equation other than to introduce some convenient algebra. I'll just write it this way. So this whole thing equals that. OK, so then the next step is to start putting stuff together. Again, we're just trying to get to a form that's like a little bit more useful. So the algebra there is partial u partial t plus 2 u partial x plus v partial u partial y equals 1 over rho minus 1 over rho times dp infinity dx plus, sorry, let me just make sure this is right. So this is nu. Yeah, so it's mu over rho, so nu partial squared u partial y squared. OK, how does that help? Well, if you look, we've now got some terms we're kind of going backwards, but this term is actually a derivative. What did I miss here? Did I miss something? Yeah, I missed something here. Sorry, let's move this over. I have the advantage of moving stuff. I know you guys don't. Sorry. So v, so this becomes plus u partial v partial y. Sorry about that. OK, so this is actually this derivative of u squared, right? So you could replace this with partial u squared dx. This is, you could use the reverse chain rule on this, and you get a different term. So again, just a little bit of algebra here would become partial u partial t plus, now this is partial u squared partial x plus partial u times v partial y is equal to minus 1 over rho dp infinity dx plus nu second derivative of u with respect to y. OK, so this is just algebra, but this actually looks more like that continuity, or sorry, the momentum conservation that we did. If you remember back to drawing the control volumes, we had momentum coming in one direction. You have the x component of or the y component of x momentum, right? That's this one here. This is the x component of x momentum. The time varying term, the pressure term, and the viscous term, right? So that just came right out of that control volume analysis. So we have this. Okay, so then the next step is to substitute in our Reynolds average stuff into this expression. Okay, so going to the next page. There it is again, what we just wrote. So let's substitute in our definitions of U and V. So again, remembering that U is equal to U bar plus U prime. V is equal to V bar plus V prime. And we could write out the full expression, but we'll save that. So you substitute that in, and we get this full expression, which is the time integral. So it's 1 over t int times the integral from 0 to t int of this whole thing. So there's a big integral here. So follow with me. It is partial of U bar plus U prime with respect to t plus partial of the quantity U bar plus U prime squared with respect to x plus the partial, the quantity U bar plus U prime times the quantity V bar plus V prime with respect to y. And that equals, on the right-hand side, run out of room again, 1 over rho dp infinity dx plus nu times second derivative U bar plus U prime with respect to y. Okay, end of that, dt. So that was our big integral. I'm missing a minus on the right-hand side here. Thank you. Anything else? Yeah, Lucas?
Why wouldn't you decompose the right-hand side times the double derivative?
Oh, this is kinematic viscosity, which I confusingly differentiate with a little preemptive hat, I guess what you call it, a little tick there. So this would be kinematic viscosity, which is rho or mu over rho. Need better nomenclature. I'm following what's in the book, just to not confuse you, but yeah. Okay, so we substituted in, just tedious stuff there. Now I guess what we want to do is go through and look at each of these terms, right? We can look at the terms and say, all right, well, off the bat, I kind of know if I break this up, du dt, or du bar dt, that's probably not going away. Du prime dt, that probably is going away, right? So we're going to go through and just kind of inspect these terms and see which of them we can throw away. So if we do that, let's see, how do I do this without being incredibly tedious? You know what, I think there's probably no good way to not be tedious. So just follow with me for a minute here. We'll write it out, and then we'll cross out the terms that we don't need. So save room. So 1 over t int, integral from 0 to t int of this whole thing. So we have partial u bar, partial t, plus partial u prime, partial t, plus partial u bar squared, partial x, partial 2 u bar u prime, partial x. Okay, and then we have partial u prime squared, partial x. We have partial u bar v bar, partial y. Okay, so then we have, where are we, partial u prime v bar, partial y, almost there, plus partial u prime v prime, partial y dt. fit dt in the end there. There's a dt, believe me. Okay, so then that's equal to, on the right-hand side, just a few things to expand out here. Again, 1 over t int, integral from 0 to t int of the quantity minus 1 over rho dp infinity dx plus v, is that new? Sorry, I can't even read it. So kinematic viscosity, partial squared u bar partial y squared plus kinematic viscosity, partial squared u prime partial y squared dt. Okay. So that was simply expanding all that crap out to this, right? So it should be the same. So our task now is to look at these and decide which of them are important and which of them go away. Okay, so I'm gonna, let's see, I'll use, let's make a green box around the stuff that's gonna stick around. So stuff that's gonna stick around would include things like average values. When you integrate the average value over time, it doesn't go away. Right? Keep in mind we're doing the time integral over here. So this sticks around. What about the next term? So the next term is du prime dt. That integral over time should go to 0. So this will go to 0. Right? That goes away. Next term would be partial of the square of u bar with respect to x. So obviously that's not going to go away. That's going to stick around. Next term is partial of 2 times u prime. So okay, we have the u prime term multiplying an average velocity. So you're still oscillating around 0. So you're just oscillating more around 0. But nonetheless, you integrate that over time, that's going to go away. So this term here, this term goes away. Let's see. Partial of u prime squared. Let's come back to that one, right? The next one. Partial of u bar v bar dy. That's let's see, u bar v bar dy. That sticks around. This one here. And let's see, we have other ones. You kind of get the idea, but we have u prime times v. This one goes away. We have u prime times v prime. Let's see, u bar v prime. Did I miss one here? Unfortunately, I did miss a term. How am I going to do this? So, okay, what we have here is this should have been partial u prime v bar plus partial v prime u bar. In the end, they go away. So okay, so I missed a term. There's another term here, as I said. It goes away anyway, so we don't have to worry about it. Okay. Right. This part is tedious for both you and for me. So okay, so we have another term here that went away. It was another term in there. What about this one here at the end? So we have these, let's say, this one here and this one here that let's talk a little bit more about. So if I take something that's oscillating about 0, positive and negative, and I square this term, right? Everywhere I square that term, and then integrate that over time, is that going to be 0 or not? No. It's always positive, right? It can't be negative. It's not symmetric around 0, or it's not stationary around 0. So this cannot go away. What about this one? It's kind of the same thing. You have x component of random oscillation, a y component of random oscillation. So I guess that one kind of depends, right? It depends on whether u prime and v prime are independent of each other. So if u prime and v prime care not at all about what the other one are doing, then they're both random, they're both stationary about 0, it would integrate to 0. However, it turns out because of continuity, right, because anytime you have a change in x, you have a compensating change in y, those two things are directly correlated, directly and inversely correlated to each other. So effectively, it acts as squaring that term. So that one can also not go away. That makes sense? So this one sticks around. this one sticks around as well. Okay, so we're left with stuff on the right-hand side then. On the right-hand side, the pressure integral, there's nothing there that causes that one to go away. The second derivative of velocity with respect to y, so we're looking at integrating something, some constant that's probably going to stick around here. And then the uncertainty term, the u prime term, that goes away. Right? This one here, so this goes away. Okay, so we've gone through this trouble, kind of simplified it down. We now have like a subset that represents our Reynolds average expression of the continuity or the x momentum equation.